Good evening, everyone. Thank you for. I would like to thank the organizer first of all for giving me the opportunity to present these results. I've been working on this. I'm a bit of an outlier in this session because I'm a theoretical physicist, and but I have an experiment to show you. So please stay with me. So I've been working on this for a few years now, since I was in University of Portsmouth last year as a PhD, and it's still an ongoing research. Now working at Politecnico di Bari in Italy. So let's start from the beginning. Two-photon interference and Gumbandel effect. I assume most of you are familiar with this. So I'll be very brief. If two identical photons impinge on a 50-50 beam splitter, you will always see them bunching together at the output ports. This is an effect of destructive interference between two indistinguishable paths, both photons reflected or both transmitted. And this is a very interesting effect for fundamental aspect, but also for application and technology. It is a known way to produce known state, for example, in a deterministic way, but also is useful for sensing and metrology, which is my interest. And so I'm going to show you now how do you use this generally for sensing. So if the two photons start to have some distinguishability level, for example, there's a delay between the two photons, you will start to observe some coincidence rate. And in particular, if you were able to scan the delay continuously while recording the number of coincidences, you will be able to reconstruct this very well-known curve. It's called Angomandel dip. It's minimum when the delay is equal to 0, and then it's maximum equal to 50% of the chance of observing coincidence when the delay between the two photons is much larger than the duration of the wave packet. So essentially what is happening here is that the two wave packets do not overlap in time anymore, so they are completely distinguishable, and so that they do not interfere. At least it is not visible interference. This curve is very well known. You can evaluate it, you can calculate it analytically, and so it is clear that if you know this curve and if you measure the number of coincidences, you can invert this function and retrieve information on the delay. This has been shown. I mean, this technique has been known for 40 years now, but recently the group in Glasgow from Ashley Lyons and Daniele Faccio, they pushed the precision of this kind of technique to the attosecond regime, which means nanometer precision. But there's a but. The but are that there's some drawbacks with this technique, and I'm going to explain you what drawback I'm talking about. So this slide I can skip, I think, because I guess we had plenty of people explaining to us in these days what some figures of merit of quantum metrology are: Fisher information and quantum Fisher information. The thing we are interested in this talk is typically the Fisher information represents the amount of information you can get in the estimation of a parameter with a given measurement scheme, whilst the quantum Fisher information is the maximization of all the possible measurement scheme. And essentially, we can say that a measurement scheme is optimal if it saturates the Fisher information is equal to the quantum Fisher information. Yes. Okay, so what are the drawbacks I was telling you about? So this sensing scheme, as I was explaining, requires an inversion of the function, an inversion of the dip. And of course, if in this region where the delay is much larger than the coherence time of the photon, well, the function is flat, and good luck inverting a flat function. So we would expect the sensitivity of this technique to drop to 0 in this region. And in fact, if I show you the Fisher information, we see at peak a sweet spot for the delay, and then an exponential drop of the Fisher information. So this can be a problem sometimes, especially if you don't have time or resources to perform a parameter dependent calibration of your setup, or for example, if you want to live track some changes of the value of the delay. And these changes, for example, in vibrometry, you want to track the changes of the delay, and these fluctuations are larger than the coherence time of the photon. So you are oscillating beyond this region there. So the question is it possible to overcome these drawbacks? And I'm going to restate the problem. The problem, as we understand it, is we want to estimate a parameter, a physical property, which is the delay between the two photons, that is quantifying, in a sense, a level of distinguishability between the two photons. But we are using an interferometric technique which relies highly on the indistinguishability between the two photons. And so the idea is it possible to conceive a different measurement which in a sense is blind to this distinguishability, regardless of the size of how large is the delay between the two photons? And this is the proposal. Of course, the answer is yes. And the proposal is we replace the detectors from bucket detectors to detectors that are capable to resolve the frequency of the photon. And why the frequency? Well, because the frequency is the conjugate variable to the time. And essentially, the idea is that these detectors are essentially blind to the time distinguishability. And what we show is that actually the Fisher information associated with this setup, when you resolve the frequency, for example, with a diffraction grating or a dispersion fiber, it saturates the quantum Cramer bound. So it is optimal. It is an optimal measurement. And I didn't tell you this before, but the quantum Fisher information is constant, does not depend on the delay. So in principle, we know that we can estimate the delay independently on how large it is, way larger than the coherence time. And this measurement saturates the quantum Cramer bound. So you can estimate the delay independently, even in the region when the two photons do not overlap in time anymore. What do we see in an experiment though? So in the experiment, if we were to perform an experiment, we would not observe anymore just the number of coincidence of bunching, so a number, but now we have a whole function, a whole distribution of probability, which is both discrete and continuous. Discrete because we are still measuring coincidence and bunching, anti-bunching events, but also continuous because we are also measuring the frequencies. And if you plot this probability distribution, we can see some beatings, fluctuations. When if you plot it against the difference of the frequencies that have been measured, and in particular, the interesting thing is that this quantum beat, the frequency of this quantum beat, is proportional to the delay. And this is true regardless of how big is the delay. So you see an effect in your probability distribution, which depends on the delay, independently on how big it is. And you'll see this fluctuation faster and faster, the larger is the delay. As you can see, the Fisher information here is equal to the quantum Fisher information. Now, I have to be clear. This idea of resolving the frequencies in a two-photon interference, or even the presence of these quantum beats, is not a new idea. It's not a new thing. There's extensive literature about it. The novelty of the result, in a way, is the understanding of the metrological power of this approach of resolving the frequencies when you do two-photon interference, and in particular, acknowledging and understanding that this technique allows to estimate the value of the delay in regions when the delay would be impossible to be measured with a standard on-command technique. So now this is to gain back your attention. I will show you the actual experimental implementation of this protocol. This has been performed by the group of working in Matera, Italian Space Agency. Luigi Santamaria Amato is the lead PI, is the lead experimentalist. And so yeah, the proposal is a bit different from our theoretical proposal because they are using a laser, not a single photon source. So they have to cancel out the first order interference. But anyway, they used they used a SPAD array with 6 or 7 pixels that were useful after a diffraction grating to measure after a beam splitter, to measure coincidence rate, bunching rate, and also resolving the frequencies. So now we had to add to develop a bit the theory to describe this kind of setup, because of course in the experiment we have a SPAD array with pixels with a finite width. And so, of course, the frequency resolution was finite in this case, and not in a sense infinite, as we were supposing or were assuming in our theoretical results. But however, so we perfection the theory, and we see there's a very nice agreement between the data and the theory. In particular, here we are plotting the number of coincidences while varying the time delay, scanning time delay, and all these figures, they represent different pairs of pixels. So this is for same pixel, pixel of distance 1, pixel of distance 2. So we are increasing the distance between the pixel, which means we are increasing the difference between the frequency that have been resolved. And the new part of the theory is that these oscillations are a bit damped, and this is an effect we show of the finite resolution of the frequency of the detector. But we show that regardless of this behavior, this damping, the effect of the resolution of the frequency, even if the resolution is finite and not infinite, it's still there's still an advantage compared to non-resolving technique. And for example, here we show plot the Fisher information for different values of resolution power of your camera, of your pixel, and we see that and there's this transition from non-resolved to ideally perfectly resolved, and the tails of the Fisher information become larger and larger for larger delay. So we still see an advantage. We can still measure delays that are much larger than the coherence time of the photons if you resolve the frequency, even if you have a finite frequency resolution. Okay, so this was the main thing I wanted to show to you. So the few seconds left, I can just it's just extra time. So I'm going to just show you very quickly that this technique, this two photon interference technique, is not really, it's very generic. It's a very generic approach. And this can be employed not only for the estimation of time delay, as it is typical of Fongo Mandel, but for any physical property. Depends on only your fantasy is your limit. And for example, in this proposal, we are measuring the position, the relative position of an emitter, of single photon emitter, which is, for example, labeling the position of a molecule. And the idea is we are resolving the two photon interference in the far field, which essentially mean in the conjugate variable of the transverse position, which is the transverse momentum. And so very quickly, we can also show that in principle this technique is also super resolution technique. We can use it to estimate the distance between two thermal source, employing always two photon interference, but it requires, I say in principle because it requires some high level of indistinguishability between two photons, which can be a bit problematic. And if you're interested in this line of research, we also performed some study about the role of entanglement and the possibility to estimate also polarization parameter of the photons. In this case, also is multi-parameter because we estimate two parameters simultaneously. But that's it. Thank you.
Thank you for this very interesting talk. Any questions? Yes. Okay, thank you. Nice talk. But please, could you show the picture when you are presenting this Fisher information? It was somewhere here. No, the problem here, I see a little problem here. If you are deriving the information from correlation measurement, you cannot distinguish what is first and what is later. So it means that it's a little bit misleading to put this on both sides. And in my opinion, what although problem this behavior on zero, there is no dip there. The point is that there is strongly biased regime. So fair interpretation should be simply to go to certain points and then start or discuss this bias regime where there will be, the error dominated by something different, not just this Fisher information scaling. Would you agree with me or not?
Yes, thank you. This is a fair observation, but in our not exactly in this experiment, but in our theoretical proposal, we do perform a maximum likelihood. We simulate numerically a maximum likelihood estimator.
But
Yeah.
the point is max leak is in general, in some cases, if you are really very close to the boundary, strongly biased, and it just happened somewhere near the zero. Yes, because zero Fisher information, actually, what does it mean? Because if you see something like that, you know that your pulses are overlapping. But it's just comment. Actually, I've talked about this with Vincenzo Tommaso.
But
Okay, so it's my comment
thank
here
you.
as well.
Thank
Sorry.
you.
Thanks. Other questions? Yes. That's last
So technologically speaking, like because you have the limitation of the frequency resolution, right? So you have achieved like picosecond resolution. But I think even with like a normal translation stage that you can scan time to the micrometer, you can also achieve that resolution now, right? So
What is the
so
question?
if you have like a just like a typical scanner that you are scanning time
Yeah.
by just moving your stage with like micrometer, you still can achieve like picosecond resolution with time scanning, I guess.
Yeah. Well, I don't know if I understand the question correctly. You're saying that the resolution in scanning, the mechanical scanning of the delay is of the mechanical scanning is here in this case is not essentially required. In from a methodological perspective, you have one value of the delay, which is given by whatever. Essentially, you're sampling. You put one photon is going through a sample, for example. The other is your reference photon, and so the sample is introducing a delay. So you want to estimate that delay. You don't need to scan anything. So you have one value of the delay. You are able only from that statistic measuring coincidence and bunching rate and resolving the frequency, you are able to estimate the value of the delay. Here we're performing a scanning just to show that we can reconstruct this theoretical predicted behavior with of the coincidence counts. But again, in an experiment, you would not collect this data. You would only have be at one point. Okay.
Right. Thank you. Yes, let's move the rest of the discussion to the coffee break. Thank
Thank
you.
you.